Here we go. This is Mr. G Math, right? Coming at you live. Room 7202, lesson 1-4 on limits and continuity. So, what is a limit? So, informally, a limit is a y value which a function approaches as x approaches some value. You can get a mathy definition, which is fine. The limit of x as it approaches c of f at x equals L means as x approaches c, f at x approaches the y value of L. You understand that a limit, it's not the destination, right? But the journey as it gets there. What is it approaching? So, let's look at number 1. How would I read that? It's the limit as x approaches -4 of f at x. So can you see where x is -4? Go to your graph. Follow it from the left and from the right. Do they agree what the y coordinate is? Yes. And what answer is that? 1. Done. Number 2, the limit as x approaches -1. Can you see where -1 is? Yeah. Go from the left and from the right. Does it agree what the y coordinate is? Yes. Do you recognize that the actual value of the function's way down here, right? At +1? But it doesn't matter what it is when you get there. It's what it's approaching that matters. Number 3, what's the limit as x approaches 2? 1. From the left and from the right, they both agree. The answer is 1. The f at x as x approaches 3?
Does not exist.
Right. It would not be incorrect to write down -infinity because both sides agree. It also wouldn't be incorrect to say does not exist. Because there are those that probably rightly think that you can't approach -infinity. Like approaching the end of the universe kind of thing. One day we're going to approach the end of the universe? Okay. Limit as x approaches 5.
Does not exist.
So from the right and from the left, do they agree on what the y? So with the jump there, that's why it doesn't exist. 6, a one-sided limit. That's right, because of the jump. And they don't agree. Left side doesn't equal right side. What does that little negative mean on the 5? From the left. So 5 from the left is what y coordinate? Try again. 5 from the left. What's the y coordinate from the left that it's approaching? Got it? And then from the right side, that little plus means from the right. What y coordinate is it approaching? Function values, 8 to 12, are not limits. What's the value of the function at -4? So at -4, what's the value? Because they agree, because the limit and that agrees, it means it's continuous, right? At function value at -1, do they agree, 2 and 9? No, that means it is not continuous. The limit exists, but the function is not continuous. At 2, does not exist. And again, they don't agree. So it's not continuous. There's a hole there, right? What's the value of the function at 3? Good. And what's the value of the function at 5? 2. Good. Continuity. Informally, a function is continuous where it can be drawn without lifting a pencil. Remember we were talking about that? Roughly, continuous just means it's fully connected, right? As you go left to right? Yes. There's no jumps, no breaks. Yes, yes?
Yes.
Okay. Formally, a function is continue, and we talked a bit about this, where its limit and function value are the same. So if it has the same limit and the same function value, if they're equal to each other, then it must be continuous. In this course, we will work with 3 types of discontinuities: holes, vertical asymptotes, and jumps. Can you picture what each of them mean? A hole. If I look at the picture above, which one can you see the hole?
Yeah.
That also creates a jump. Do you see that? So technically here is a jump. Well, this one here is a hole. Here again is a jump. And then we have then vertical asymptote. So jumps, holes, and vertical asymptotes. So in example 13, list the x values of the discontinuities of f at x. So where's the function not continuous on that graph above? When x equals what?
1.
Negative 1. What else? 2. And what else?
3.
And what else?
5.
And 5. So there are 5 x values where it is not continuous. So all discontinuities can be classified as removable or non-removable. Remember how we defined it? Removable occurs when the function still has a limit. So can you take a limit at that discontinuity? It means it is removable. Can you not take a limit there? Then it is non-removable. So what's the indicator to know if it's removable or non-removable? Limit. Does the limit exist or not? Got it? So in example 14 it says, which of the following discontinuities are removable? So where does the limit still exist? At x equals negative 1. Where else does it still exist, the limit?
2.
At x equals 2. Any other ones?
5.
No. At 5 the limit didn't exist, right? So only at negative 1 and 2. At x values where a function is continuous, limits can be found by direct substitution. So what's the first rule of finding a limit? You plug it in. If you find that it is indeterminate, then we have to use some algebra. But what's the first rule of a limit? Plug it in and see if you get an answer. So for 15, if you want to find a limit analytically, no graph, what do I do with the 3? Plug it in. So can I plug this in and get an answer?
Yeah.
It's 27 plus 2. So what does that say about the function around 3? Is that it's continuous, right? The limit and the value of the function agree with each other, right? 16. Again, what's the first rule to find a limit? It's just to plug it in. If you find that it makes it undefined or indeterminate, then you have to use algebra. 1 squared plus 1, 1 plus 1. What's the limit as x approaches 1 analytically? And how did you find it? Analytically rather than off a graph? But just substitution. Turn the page.
So now what does that mean? That it approaches, as the limit approaches
As the limit as x approaches 1 of, and you write it down, right? In this case, of x squared plus x all over x plus 1. So you're saying how to read it?
No, so what does 1 signify as in our solution?
Oh, the solution is the y-coordinate. So as x approaches 1, the y-coordinate approaches 1. Now in this case, it also equals 1, right? Like when you get to the destination, that's not the limit. So for the limit, what's the value here? As x approaches 1, what does y approach? 1. That's what it's saying. Turn the page. And the concept of a limit is new for everyone in this room. Piecewise, don't you love them? In these examples, how would you find the limit? So here's a function defined by piecewise, and it says find the limit as x approaches 1. I want you to know that 1 is where the pieces come together, right? That means if the limit exists, the right side still has to agree with the left side. It doesn't matter at 1. It matters from the left and the right that they approach the same number. So I have to plug in 1 on the top. And what do you get? So I'm going to do that on the side. What's f at 1 from the top? What does it equal? 3. So if I plug in that, what happens if I plug 1 into the bottom? Still 3. Do they agree that if I plug it in here, it's 3. If I plug it in here, it's 3. They agree. So what is the limit then? If they didn't agree, you would say the limit does not. If it says it's one-sided, then you have to know what's the left and right side. So the above one would be the left and the bottom would be the right side. So here's another example. When you plug in 1, do you notice that's where the pieces go together? Now, if it said not number 1, but if it said like 2 or 8 or negative 12, what would you do? You would plug it into just the piece, right, that you need to? So if it said 2, you would just plug it into the bottom. Why? because that's the only place where 2 is valid. The reason we're using both is because that's where the two functions meet. And the left and right have to agree. So if I plug 1 into the top, 3 times 1 and 1 cubed, so 3 take away 1, the top is 2. Plug 1 into the bottom, 1 squared times 2, and 2 take away 1, what do you notice? Do they agree?
No.
1 was 2, the other was 1, so this one, if it was a left-handed limit, the answer would be 2. If it was a right-sided limit, the answer would be 1. But the limit doesn't exist because they don't agree. Left side does not agree with right side. So for the same g function, what's the limit of g at x as x approaches negative 1? Do you see that? Well, for negative 1, that's only valid for one piece. What's the one piece I'd plug it into?
The top.
Only the top. That's it. I don't need the bottom piece. Because negative 1 is not valid in the bottom piece. So just the top piece. 3 times negative 1, negative 3. This is negative 1, but a negative and a negative make it plus 1. So it's negative 3 plus 1. Negative 3 plus 1. So it is negative 2. So be aware of the domain, right, of which one you plug it into.
So that means as x approaches
So as x approaches negative 1, the y-coordinate is negative 2. When's the only time you'd have to look at both for piecewise? When that x value is the connecting x value, right? See how it connects both, positive 1? That's the only time you would use both. Otherwise, you'd use one or the other, knowing what the domain is. We'll practice that. Okay, last one. Another function requiring one-sided limit analysis is called a step function. How many of you have ever seen a step function before? Right? All my pre-cal honors students say yes. Why do you think it's called a step function? They look like steps. So the official word is called the greatest integer function. What's the greatest integer less than or equal to, whatever that is? What's the symbol for that greatest integer function? The double bar. So if you look at it below, it looks a little different, right? So in other words, can I help explain the function just a little bit more? Let's say that you pick the number between 0 and 1. First of all, do you know what integers are? They're whole numbers that are negative, 0, or positive, okay? Whole numbers. Fractions, decimals aren't integers, yes? So if I said positive a half, right? What's the greatest integer less than or equal to a half? And what would you say? 0.
Oh.
You know what I'm saying? If I said 1.5, right? 1.5, what's the greatest integer less than or equal to 1.5? 1. It's confusing because they put two fun words together. Greatest and less than or equal to, right? And they're kind of opposing each other. Anyway, that's where you get steps. Where do you actually get jumps is at actually the integer. So at every integer, there's going to be a jump to the next integer. What's the limit as x approaches a half? So look at the graph. Look at where half is. Look from the left and right. Do they agree on the y-coordinate? Yes. And what's the y-coordinate? 0. What's the limit as x approaches positive 1? So do you see positive 1?
Yeah.
Do you see at every integer there's going to be a jump? So in this jump, it doesn't exist. But here's the challenge. If it said from the left, the answer would have been 0. From the right, the answer would have been positive 1. So that you have to think a bit when it lands on an integer. All right, Mr. G Math, over and out.